can't be forgiven.
You seem like a pretty intelligible guy, Joey. Can you tell us about the impulse momentum theorem as well as the law of conservation of momentum?
Nah, man, you got it.
Alright, boys, so basically with conservation of momentum, or law of conservation of momentum.
That's enough of that. We'll demonstrate the law of conservation of momentum first qualitatively by shooting one puck into another stationary puck. When the first puck strikes the second, both will experience a change in momentum, the exact details of which will depend on the elasticity of the collision. Regardless, according to the law of conservation of momentum, the final momentum of the system will equal the initial momentum. At this point in time before the collision, we can see clearly that puck 1 has a velocity in the positive direction, whereas puck 2 is stationary. Note that both pucks are identical, meaning they share the same mass. After the collision, puck 1 transfers some of its linear momentum to puck 2, which now has a velocity in the positive direction. Note that puck 1 did not actually hit puck 2 perfectly along the x-axis, but we will model it as if it did. If we perform some simple vector addition, it is clear that this situation does accurately represent the law of conservation of momentum, as the initial velocity of puck 1 plus 0, or the initial velocity of puck 2, is equal to the sum of the final velocities of puck 1 and puck 2. Since both pucks have the same mass, comparing the pucks' velocities is equivalent to comparing their momentum.
Go. Impulse, boys!
To show impulse momentum theorem qualitatively, we'll shoot a puck such that it first travels through relatively frictionless ice, thus conserving its momentum, and then it reaches snowy ice, which will exert an impulse on the puck in the opposite direction of its movement, decreasing its momentum. Here we can see the clear difference between the smooth ice, which is nearly frictionless, and the snowy ice, which is not. As the puck enters the snowy ice, the impulse from the snow acting on the puck obviously reduces the puck's momentum in the positive direction. According to the impulse momentum theorem, the change in momentum of the puck is equal to the impulse exerted on the puck, which is also equal to the average net force acting on the puck multiplied by the change in time during which the force was acting on the puck. Now, we will discuss the law of conservation of momentum in more detail. To demonstrate the law of conservation of momentum quantitatively, we will use data from an in-class lab. In this specific trial, we pushed two carts of varying masses across a nearly frictionless surface at different velocities. We measured both the initial and final velocities of each in order to determine both the initial and final momentums of the system. As you can see, the mass of the red car is just over double that of the blue car. Further, the velocities of each car are nearly identical in magnitude, just opposite in direction. Using momentum equals mass times velocity and adding the initial momentum of each car, we can find the initial momentum of the system to be 0.09 kilogram meters per second. After the collision, the velocity of each car has substantially changed, each traveling in opposite directions to which they began. By following the same process we used to find the initial momentum of the system, we find the final momentum of the system to be 0.082 kilogram meters per second. Theoretically, the initial momentum of a closed system should be equal to its final momentum according to the law of conservation of momentum. However, there will always be errors in real life. To calculate the percent error of this trial, we can let the variable x equal the coefficient with which multiplying the measured initial momentum of the system will equal the measured final momentum of the system. Once numbers are plugged in, x is equal to 0.91. Using this value and 1 as the accepted value, we can do a simple percent error calculation, which will yield a negative 9% error for this trial. This is a linearized graph of all of our data points from the conservation of momentum lab, with the initial momentum of the system being plotted on the x-axis and the final momentum of the system being plotted on the y-axis. At first glance, it appears that we have a high percent error, as our slope is only 0.59 as opposed to the predicted value of 1. However, we have determined this to be a result of these outliers that are circled in red. We determined these points to simply be bad data, the specifics of which will be outlined in our lab report. Upon removing these points, our measured slope becomes considerably better, as a value of 0.97 yields only a negative 3% error. The vast majority of our data points follow the desired trend. Here is the table with all of our data. Pause if you would like to go through it. Next, we will discuss impulse momentum theorem in more depth. Unfortunately, I do not have access to any videos of our trials during the impulse momentum theorem lab, so these diagrams will have to suffice. First, we push the cart along a nearly frictionless track towards a force probe. When the cart collides with the force probe, the probe will enact an impulse on the cart, thus changing its momentum. The final momentum of the cart after the impulse can be seen in the third image. For each trial, we would repeat this process with varying initial velocities and masses. For this lab, we measured the mass, initial velocity, and final velocity of the cart, as well as the impulse exerted on the cart by the force probe. First, we will use the equation momentum equals mass times velocity to calculate the initial and final momentum of the cart, which allows us to calculate the change in momentum, or delta P, to be negative 0.571 kilogram meters per second. By using the integral function on the lab quest, we obtained a value of negative 0.538 newtons per second for the impulse. According to impulse momentum theorem, change in momentum is equal to impulse is equal to average force multiplied by the time interval during which this force is applied. Since we didn't measure force nor time, we will only use the first two parts of this equation. By finding the ratio of the impulse to the change in momentum, we obtain the experimental value of the slope for this trial, which is meant to be 1 since impulse is theoretically equal to change in momentum. By doing this, we obtain a value of 0.942, which results in a negative 5.8% error. Here is the graph in which we plotted our measured values of impulse on the x-axis and our measured values of change in momentum on the y-axis. Clearly, our slope of 1.4373 is not accurate to the expected value of 1. After much consideration and testing, we discern that the cause of this error to be variations in the reading of the force probe. We go into more detail about this source of error and others in our lab report. Except for one notable outlier, all of our data points seem to follow our trend line, meaning that if our force probe functioned properly, we would likely have a low % error. This is our data table containing all data we measured for the impulse momentum theorem lab. If you would like to study it, please pause the video. Thank you for watching the video portion of our group's momentum project for AP Physics 1.